Greetings and welcome to a new video about 2 degrees of freedom of PID controller design. This is our example number 2. In this example, we'll again continue as we did in the example number 1 using step-by-step calculations, and we will verify these in MATLAB using MATLAB simulations. Okay, let's look at example number 2. Given the open loop system G in 2 degrees of freedom as shown here in a control system, and the plant is in this case given a more complicated form compared to example number 1. You have now actually a 0, you have 1 pole at the origin, 1 pole at -1, and 2 poles given by this expression. What we want, as we did also in the example number 2 and 1, we have the response to a unit step disturbance specification must be small and it must settle to 0 in less than 2 seconds. The response to unit step reference input has a maximum value of overshoot of 15%, and a settling time with a 2% criterion must be also less than 1 second. The steady state errors for the step, the ramp, and the acceleration reference inputs must be 0. So for all 3, we need to have a 0 steady state error, or the final value must be what it is actually what applied. Okay, so how do we continue and what is the procedure here? So let's first again look at the closed loop transfer functions. Then we can of course use the characteristic equation and then use the design point and the further steps. First, the reference to output, so the reference R to Y, just considering that, is this closed loop transfer function, which is of course given by this configuration. And if you look at the disturbance, just focus on disturbance and you disable the R, then you will have this expression. And these look of course the same if you just look at the denominator where you see 1 plus the controller 1 times the plant. And that is actually also the characteristic equation we will use. Now step 1 is you just consider the disturbance only and then assume for PI for the controller 1 as a PID controller. In this case we also add a filter. We have discussed this filter also in the introductory part of example 1, so we will do that here. You are not actually stick to this formation. You can also use another controller for controller 1. This is just an example to illustrate the idea of 2 degrees of freedom controller design. So we have now this controller for the controller 1. Again, we see 2 zeros at the same location, 1 pole at the origin, the controller gain, and this A is a sort of a filter. In this case, we have already chosen the A. Of course, it's a specific value. You can see it is chosen actually with the numerator, which is the denominator of the plant, in order to cancel that and make that actually work for this specific part. You can also see that one of the poles is the 0 of the plant, and we have in addition another pole of the filter which we'll then use later on for our analysis. Now the lowest equation is then given for this situation: 1 plus the loop transfer function LS is equal to 0, and that will be of course just this controller C1 times the plant will be equal to 0. If you now substitute everything we have, you will have this, and we see we lose this. We also, because of this, we lose S plus 8, so that's all gone. Only part we have actually here from the A is S plus 20 and S times S plus 1, of course the 5. So in total you will actually get this, so you will lose a lot of stuff, and you will have in the simplified form this locus equation. Okay, from the specification, that's also important. We know that the MP must be 15% or 0.15, and then the damping ratio will result using this formula. We have done it also many times in the previous videos, is 0.517. Now the settling time of 1 second will result in a sigma d, which is then the absolute damping of 4 radians per second. Now then we can use the omega d, which will then give us the imaginary value of our design point. We'll be then using this formula, 6.6 radians per second. Now then the design point is given by this general expression, and if you now substitute everything you will get -4, which is just this sigma d, and then J plus J 6.6. This is our important step here, and we know now the design point. Now next thing is looking at our angle condition, because the root log equation wants to have two conditions, angle condition, and we have also the magnetic condition, which will be done after this. Now before we move on with that one, we first make a sketch. We'll give the real and imaginary axis, and we know the design point is given here, and we know also that the design point can be designated there in this plot. So we have the J6.6 as imaginary and -4 as the real value. This is the PM. Now for future reference, we also know that this is our root locus equation, and from this we can locate where our poles and zeros are, which is of course determined will determine the parameters for A and the K1 using this design point PM. Now let's first then start with the pole at the origin. We have a double pole. You can see that form S squared. So S equal to 0 will give us, we have two poles there at the origin, and that will make a phase contribution, and I will call phi 1 is equal to phi 2. So we have two phases there due to that double pole at the origin. So two pure integrators. We have also a pole at the -1. You can see that here, and it will also contribute some phase, and that will be called here phi 3. We also have, of course, the 0 of this. This is now -a here, and it will also contribute phase here. That is actually a double 0, so double PID 0, which is then shown here. This can be also, of course, placed here on the left hand side, depending on the value. I just place it here. We will see if we need to shift it to the left hand side. If this is, of course, a value for the phase, so this phi A, if this is larger than 90 degrees, this location is correct. If it is between 90 and 0 degrees, it must be in the left hand side. We also know that we have -20, that's also fixed for our pole, which is due to the filter, and that will be then the phi 4. So we have now all the necessary phases and also the lines connecting to that design point. So the angle condition, we said -phi 1, all the poles, by the way, will contribute negative phase, and all the zeros will contribute positive phase. So that will be negative here, negative, of course, 2 times negative, here also negative. We also have a negative here, and we have done 2 times the positive phase contribution there. That's also shown here, -phi 1, -phi 2, -phi 3, -phi 4, plus 2 times phi A must be -180 degrees. This is the condition we need to meet in order to have that root locus equation complete. Okay, now phi 1 is the phase contribution of the planned pole at S is equal to 0. We had that. We also phi 2, which is the phase contribution of the PID pole, again at the origin, S is equal to 0. Phi 3 is the phase contribution of the planned pole at S is -1. Now we have also the phase contribution of the filter pole at -20. That will also have an effect. And we have the phase contribution of the double PID 0 at S equal to -a. Now let's now calculate each of these and then see what the required value here is, because the location here is not yet determined. We all know the location of the others, the poles. Okay, now again we do that as we did in the previous video. What we do is, of course, in order to calculate this angle, which is of course larger than 90 degrees, we calculate this angle, which is a sharper angle here, and then we do 180 degrees minus this angle, which is actually shown here. So a height is 6.6 divided by 4 in the arctangent formula, and then 180 degrees minus that will give you 121. In exact same fashion, of course, is the value for phi 2, because those are exactly equal to each other. In a similar form, phi 3, exact same format, then of course this will be 3, and that will be 114. Now, this angle is much smaller, and of course only this, because it is a sharper angle between 0 and 90 degrees. You don't use 180 degrees minus 0, etc. You just use arctangent, and it will be then this value. And because this distance is required, we do 20 minus 4. You will have 22 degrees for that phi 4. Now let's check then what we have. We have, of course, now 4 elements, the poles, and then of course the 2 times the location of the 0 for the phase. Now everything added, and then plus 2 times the phi A, it will be minus 180 degrees. If you now do the math, you will get 99 degrees. So that is indeed larger than 90 degrees. So that will be, this will be of course in the sketch the correct location. Okay, then what we have the following, we do now in order to calculate now this value, we will again use this angle. Well, for that we of course need to do 180 degrees, so half circle minus this, and then use again the formula for the tangent, which is then the height divided by this distance here, so which is then 6.6 divided by 4 minus the a. Now if you do now the calculations, just substitute the value for phi a, and then you will get for a 2.95, almost 3. Okay, that is the first step, and we now know for controller 1, the PID controller, that the a is known, and the small letter a, this is then the 0, we have 2 zeros at minus 2.95. We don't know yet the controller gain K1. We also know the filter, which is of course the a, it was already given, so if you add them up you will get this complete expression, except of course the K1, which is then the next step. Okay, that is the controller 1, and we are close to the complete expression. Again, this is the expression, or the plot I mean, and again everything is now known here, so we can now use the magnitude criterion or the magnitude condition. The magnitude criterion or the magnitude condition says the following: the root locus equation again will be used. This is of course what we had, and we just substitute everything in it, also the plant. That will again reduce to this one, because this s plus 8 and s plus 8 will cancel each other out. This expression of the s squared, etc. will also cancel this s squared plus 4s plus 13. So you will have actually much easier expression here. And it will give you the following expression. So K1 is now expressed in the rest of the parameters. You know that's also here. So what you then do is you need to evaluate K1 at the design point, which was minus 4, J 6.6. So if I do that, evaluate this, and again of course take the absolute value in order to have the real value in order to use that, we will have then the following situation. You can see the minus 4 plus J 6.6 is now inserted here. It's also here. This plus 1 was already there, and plus 20 was also already there. So this is now the complete situation, just inserting actually your PM, your design point. Now simplifying this, because you can of course make this minus 4 and 1 or minus 3, so everything all else were also in a similar form. Now we need of course have a magnitude, so we need to take the magnitude of each this. So you take the magnitude by taking the square root of the real part squared plus the imaginary part squared in a similar format here, and you will get a result which is then 33.5. Now then the controller 1, which is then the PID controller, of course in cascade with a filter here, which is then given here in blue, will be then this, and then using the K we have just determined will be then this expression. This is now our controller 1. That is actually for the first controller. Okay, moving on, and again showing the root locus plot with all the necessary elements. We can now say the controller 1 is this. That can be of course rewritten in a different form, such that we can recognize the P and the I and the D forms. Now what we do is just of course leave the filter as it is, just focus on this part. So 33.5 will be multiplied here, so the s squared will be multiplied by this, and also the other two terms in the numerator. You will get this by dividing by s, and you can see the P is then 198. The I is actually this part, which is then 291 over s, and this is the derivative part, which is then 33.5s. This is then the PID controller, just native, and this is now the cascaded with a filter. So the closed-loop transfer function now, just looking at the disturbance to output transfer, which is then given by TYD, will be then this expression. We know the G, that's just the plant, and we know also the controller now. We can substitute everything in it and then simplify. We get the following expression. This is now the expression we can use in order to set up or produce the response, the step response for the output, considering only the disturbance. Okay. Next step is considering the reference signal, because we have the reference and also disturbance in our diagram. So the closed loop transfer function was given for that, as shown here, from reference to y, so y over r, which was given here. And if we now define this combination, which is actually the summation of the two controllers, as just the total controller, then we have this more simplified expression. Then this will be then, if you just add everything out we know so far, of course the controller we don't know yet, full controller, but we know the plant, we also know the GC1, the controller 1. Now you add them up, you get this huge expression. Of course you can again cancel these, you can again cancel also these, so you can make the expression much easier to see. And this will be then our transfer function, which will then give reference to output transfer. This will be, of course, then can be written in this form, so the denominator stays the same. Numerator, I mean, the denominator, you can see it is actually worked out such that it is shown as a polynomial, so it is now a fourth order polynomial, s to the power 4 up to a constant value. So we have now here 5 terms. Why is this done? Because we need to use the zero placement approach. In order to do that, we need a polynomial instead of the expression shown here in brackets or parentheses. So the zero placement approach, what we do is we choose the numerator of this equal to the last 3 terms of the denominator of, again, the same expression. That is a zero placement approach. So thus we have this is equal to the 198 s squared plus etc. You get this one. Now if you now work it out, just looking at the total controller, you will get actually this right hand side divided by this left hand side coefficient, except of course the GC. Then you will have this. Now this is now the expression you have, and if you now look at it, you can again recognize that there is a expression for the filter. And this is now the given by this orange part, and you can of course divide everything by 5, so only step from here to there. So if I go back, this from here to here is only part which is now actually changing is this, and this will be divided by 5, so it's much more simplified. Okay, then the controller 2, because we know the controller total is controller 1 plus controller 2, so controller 2 is then controller total minus controller 1. Straightforward analysis. So we need to know this green, so the controller 2. If I now substitute everything we have, so the controller in total we have, and controller 1 also we already have determined that from the previous analysis. These are the values, for the expressions for that, and if I now simplify this, I will have this 6.1s times again the filter. So that means the following: each of the controller 1 and controller 2 has in cascade the given filter A, which is then given here in brown. Okay, now total result. This is the configuration, and these are the controllers we have designed. This is the controller 1, GC1, and then given different format, and this is the GC2. You can see all of them have the filter A in cascade. Now this will be of course then transformed in this form. You can see using the controller 1, you can of course use this configuration, which is the PID, and then in cascade this, but since this is the same for the controller 2, which is shown here, you can of course also bring this filter outside and then add them up first, the controllers without the filter, and then multiply by the filter. That will give you exact same result. This is the plant, this is the part where the disturbance is placed, and we have the unity gain feedback configuration again. So we have the PID controller and also the D controller in cascade for that, the filter. Alright, this is now what we have achieved. Of course we need to verify this. Let's then look at the simulation results, and we start with first the unit step, the response, considering the disturbance only. What we see is the following result. We have of course in the specification given that the disturbance step response, so the step disturbance must actually have a small peak. Of course, it is not designated precisely what small it means, and it must settle to 0 in less than 2 seconds. Of course, we see a peak here, which is then 0.0523. For a unit input, we get only 0.05, so it is quite small if you compare it as that. And I need, of course, we need to have a 0, it must settle to 0 in less than 2 seconds. If I look at 2 seconds, it is not 0. It is, of course, starting here 0, but then, of course, it goes up and then go down. But it is quite small here already, very, very small. So if I look at, let's say, 4 seconds, which is, of course, 2 times larger, but it's already minus 2.9 times 10 to the power minus 5. So it is approximately, in absolute sense, 29 micro in whatever this amplitude unit is. So let's say in volts, so it is already 2.29 microvolts. So it is very small actually. So I think we can assume that this condition is also met pretty well. Okay, this is for the disturbance, you can see, and this is then for the peak, and this was our closed loop transfer function from disturbance to output, and this is the result again. And in this case I say 0 in 4 seconds. Of course, it's actually a little bit earlier. Now let's also look at the reference to output, which is then this response. You can see this is the response total YR. You can see the following information again, the specifications, 15% settling time of 1 second, and I can see that it is 55.4%, which is definitely much larger, at least 3 times larger, so that is no good. And we have the settling time, which is 1.11, which is, yeah, it is not close, but also not disastrous. So this is dramatically larger, but this is, of course, also larger, but not that large. But it's also not good. So we need to be, of course, in the limits. So we need to make that also 1 second or smaller, and this also 15% or smaller. The final value is fine, that's 1. So that's one of the things we surely achieve using this configuration for the controller. So in total, 55.4% larger than 15% and 1.11 second also larger than 1 second. So we need to fix these 2 specifications to get here. So how do we do that? This is, of course, a challenging situation because the overshoot is much, much smaller. So it is quite a challenge, probably, to lower this and also get that 1 second settling time. So let's see what we can do. So let's also look at the root locus and the reference to output, because that will also give you some idea. This was, of course, the root locus, and this is focusing only the response to unit disturbance input. You can also see from here, from R to Y, which is actually shown in MATLAB. And again, same business also shown here. You can see this is the design point, which is also shown here. So in the right bottom here, so minus 3.9 approximately, and then plus 6.74i, and we had minus 4 plus J6.6, so it's very close. But our damping ratio was also 0.5, a little bit larger than this, so it's also close to what we had. Well, of course, this is not good, because our overshoot is much larger, and also settling time is also larger. So the only thing that is now working here is the final value, but the rest is bad. So overshoot and settling time we need to fix. So we need to tune the controller. Again, this is always, not always, but most of the time the case. If you have a controller, you build it, it's not the final step. You need to fine tune this, and also in real time you need again check this measurement, and maybe again fine tune your components and your adjustment. Now, so next step is then adjusting the controller. So let's again look at our original design controllers to have the framework. We have the controller 1 here, the transfer function, and controller 2, the transfer function. What I have done is again using standard way of tuning, just one parameter at a time. Let's say the gain of the controller 1 or gain here of the controller 2, and then see what kind of response I had. So I used trial and error. After trial and error, of course, sometimes you need to do more trial and errors. It can be sometimes trial and horror, because you really need to do and change a lot of stuff, and that can be a little bit frustrating. In this case, it was also a little bit the case, because I was not able to get the specifications done, so I cannot met the specifications just by tuning one of the parameters, let's say the gain only, or let's say the zero only, or let's say the gain of the controller only. That was not really possible. So what I have done is actually in total this one, and that's actually after several tryouts, it's not the first round. So in controller 1, I gain actually changed from the 33.5 to 137. This is what I get from tuning, not what I have made up. So this can be, of course, maybe also possible for 140. I've changed a 0 from this value to that value. This was actually the most time consuming part. So the 0 location was very hard to find a suitable 0. So I tried a larger and a smaller 0 and then tune back again. The gain was really time consuming. So in this case, I have actually found that this was okay, but then I have actually also a problem with my location of one of the filter poles, which was at the minus 20. I have also placed it at the minus 30. So you see, I have made 3 changes, which is of course not really trivial, but you can always try to do 1 at a time, and then if that doesn't fix, then do 2. And then in this case, which is of course another step forward, and I have to do another change, which is in the filter pole. You might of course try this yourself and then maybe come with another solution, maybe much easier, but this is what I have produced. Now the adjusted controller 1, will be then this one. You can see 137 and then the 0 location of 0.4, so everything is actually here changed. And this is also changed, which is one of the poles of the filter. Of course, the controller 1 is then rewritten in this format, and then I can also say the adjust controller 2, that will also change because the filter pole is changing, so that will also change. And this will then given by this expression. So the total controller configuration was this, you know, the old when with this configuration and also the filter. That will be now actually this. So you will now get this expression. This is again the result of by working out the parentheses here and multiply everything by 137. You will get this one, and again in cascade with the same filter, which is also valid for controller 2. Now controller 2 is the same, of course, the 6.1s, only the filter is changing for controller 2. The plan is the same, the disturbance, etc. is all shown here. So this is now the tune part. Again, this is of course explained now in a very short time, but the tuning here was quite time consuming. I would like to also show that in MATLAB later. Now, the simulation result for the unitary step response of reference to output, in this case having the tuned parameters for our controllers. So this is then the root locus plot. You can see that here, so some of the parameters are changed. Of course, you can see the minus 30 here, and the 0 is actually here, so it is really hard to see, but the whole action is actually also there, but also partially here. You can see now also the step response. You can see why this is, of course, doing the job. You can now see here that the specifications are shown here, so you can see the step response. Unit step response for reference give me 14.7% overshoot, less than 15%. That's fine. And I also have 0.973 for my settling times, less than 1 second, also fine. And the final value was 1. So all done. So this was a solution for this problem. Again, you can have another solution which will again make it even better. Okay, now the overshoot in summarizing your settling time and also the final value, which is of course meaning the steady state error as 0 for step input. Now moving on with the unit ramp response, then reference to output. So just focusing on the ramp, we have this. So we have the orange line, which is then the ramp input, which is a linear line. So you can see from 0 up to 1 and 8, and it goes also to 8. The response is the blue one. Now this is again the specifications here, it must be 0, so this difference here is 0. So, and again the controllers all shown here, adjusted values of course, and the steady state error for the ramp input is 0, so this will also do the job. The next step is the acceleration response for this situation, where we have of course the adjusted parameters for our controllers. This is the response. You can see it started at 0 and it goes to the value, and we have again the orange line is the R acceleration, so the input, and this is the response to that unit acceleration input. Now you can see the orange and the blue line are a little bit apart here. If you zoom in, it's already a very small error, but the error is now almost 0 when you go to larger time values. You don't of course measure that at the beginning, you wait a little bit, so at steady state it will then catch each other up, and then it will be then 0 steady state error for acceleration also. So that is of course what we have, what we require from specifications, and this is the controls again. So we know this steady state error for the acceleration also 0. Good, that is also what we had. So this is fine, and we know that we have now met all the responses and specifications we needed for this example. So let's also look at the disturbance and how does that look like. Now the peak amplitude now is here 0.125, and it is somewhat larger than before, and also you can see it has of course also a longer tail. So if I like at 2 seconds, because already it is a large value, it doesn't settle actually, so the disturbance specification is not really met. I need to admit that it was really hard, and this part is not really possible. This is fine in the sense of small peak compared to 1, it's just 0.125, but if you look at the final value, it is 0 approximately in 20 seconds, not in 2 seconds, so it is 10 times larger. That is definitely not okay, but this is something it was really hard to manage. I was already happy that I have for the overshoot, the settling time, etc., the required values. What can you do then of course to get that disturbance better? You might of course try to figure out, maybe change the value of the controller 2. That will definitely also have an effect of the rest, so it is quite hard and also interactive problem. So this is maybe already something you can just use and then try to optimize later. Okay, let's make also a comparison of the simulation results. Just looking at the reference output, the blue one was originally designed system controller, and then the response for that, you can see that was not good. And the orange one here was actually when we have tuned the controller and also of course the filter. That was fine of course, because all of them are below what we require, and also the final value was 1, so all the specifications are fine. So if I now summarize everything, controller 1 of course was adjusted, and of course also controller 2, but let's say the controller 1, the major part of controller 1 was adjusted, so you can see this was adjusted to 137, and the 0 was 0.4 instead of 2.95. Then you can see this is all then smaller than before, and also within the specifications we require. Okay, now comparing also the disturbance, I already said that, disturbance to the output. So the first case is the blue one, which is actually, you can see 0.05 approximately, and it goes very fast to actually 0 and maybe in 2 or 2.5 seconds. So the blue one is much better. But if I look at the orange one, which is of course the adjusted response, that is not actually doing the job. So it goes much higher. So this is almost let's say maybe 2.5 times larger, the amplitude, and also it doesn't settle in 2 seconds. So this settles in, let's say, 3 seconds, maybe 2.5 seconds, and this is fine. But this is sort of okay, maybe. And I can say it settles after 22, maybe 25 seconds, maybe 20 if I'm actually a bit optimistic. So the disturbance part to output, that specification is definitely not met here. So what you then have, again, just looking at the disturbance, this is the controller and this is the adjusted value. So you can see the peak value. This is then again much larger than that one. And you can see after, let's say, approximately 3 seconds, but this is then approximately after 22 or 25 seconds. All right, so we have now the complete picture, and only parameter we haven't managed to get is the disturbance, and that is of course another trial and error cycles. But I was already happy that I had managed by tuning 3 parameters and to get the overshoot and settling time done, and the disturbance is not really that high, but it's of course higher, but the tail is much longer. So there is something of course we can also win by adjusting a parameter here. Okay, this concludes the example about the unit step response of several inputs, so disturbance and reference, and also we have checked the ramp and also the acceleration for the reference input. If you have any questions about this example, please let me know and I will try to answer them as soon as possible. I will see you, of course, hopefully in another interesting video, and I will try to also upload as soon as possible the example number 3 about this topic, and also hopefully as soon as possible the example number 4 in using different configuration, also different plans. Don't forget to like and share so that we can reach more people. It's very important. Thank you very much and see you next time. Take care.